The Science of Feeding Tomorrow. Pathway Intermediates.
I would like to have a moment to tell you the difference between some terms. Probably you have heard a lot about the precision livestock farming these days, which is called PLF. Okay, the definition of PLF is real-time monitoring technologies aimed at managing the smallest manageable product unit, the individual in cattle, for example, otherwise known as the sensor-based individual animal approach. Okay, so PLF is basically technology. Another term is very famous these days is smart farming. The smart farming, smart stands for the first letter of the words self-monitoring, analysis, and reporting technology, which means it's automated, right? So smart farming, basically animal farming, use automatic technology. So PLF and us are technologies, while precision feeding is our ultimate goal. So for the precision feeding, we can use the precision livestock farm PLF for smart technology. So make sure the precision feeding is just it's not just technology, but it's kind of philosophy and our objective. So until now, I have talked about what precision feeding is and why we need the precision and modeling. Let's talk a little bit about some science of ruminant nutrition and the basis on which the current nutrition model is based. Okay, let's start with the simple basics. I always emphasize this when I talk about the nutrition. Okay, our key to nutritional process is the digestion system. Okay, anatomy and the function of gastrointestinal tract determines the digestion. Digestion is only just the process that ingested feed divide or degrade ingested feed into small pieces so they can be observed to the animal cells. Actually, the metabolism is conserved across all animals, So even human and bacteria share some core metabolism. Okay, animal cells use whatever that is observed after digestion process in the gastrointestinal tract. And in terms of digestion system, ruminants have complicated and fascinating animal, and that's why I decided to become a ruminant nutritionist. Ruminants are evolutionarily adapted to extract as much nutrient as possible from forage and fibrous feeds. And they have four stomachs, and the first two stomachs, which are the rumen and reticulum, there is no wall between these two organs, so all the digestive material can move from one to the other. And then in the reticulo, so we call it reticulo-rumen. And in the reticulo-rumen, it has a unique and a very specialized digestive system. And then in the reticulo-rumen, there are microbes. And with the symbiosis with anaerobic microbes, ruminants can survive and digest the feeds. And this table shows some figures of the rumen, reticulo-rumen volume and all other values. And this figure shows the structure of the rumen and reticulo-rumen, and this part is reticulum. And there are several subdivided sacs in the rumen, and this big the part we call it rumen, and there are a lot of microbes living in this organ, and then all four kingdoms are living here. Today I will not go too much detail about this. One of the most interesting features of reticulo-rumen is that it contracts regularly and irregularly. there are two types of contractions. Okay, the primary contraction, which is called A sequence, is biphasic contraction, and the function of this contraction is the mixing and the stratification of the digesta. The reticulum, it starts from the reticulum. So right here, from here to here is the sequence A, or primary contraction, and it starts from the reticulum. And the reticulum contracts once every minute during resting. And here is the statistics actually obtained from all the literature that while eating, the reticular contracts 1.6 per minute. Okay. By the way, the contraction for rumination occurs irregularly prior to this primary reticular contraction. The secondary contraction, which is called a B sequence, is also occurs, and it starts from the caudoventral blind sac right here. So actually, the rumen part it contracts during the secondary contraction. The major role of the secondary contraction is eructation of gas, and it contracts irregularly. This physiology is very important, and then I will briefly introduce the model I developed to describe the dynamics of this contraction and the Rumen Digesta later in this presentation. And due to this reticular contraction, stratification of ruminal digesta can be possible. And then because of these contractions, the current of digesta movement occurs. So, thanks to the contraction and digesta movement, we can have a rumen mat right here. And then because of the rumen mat, the dense materials, so it's probably, not 100%, but mostly digested materials will be located in the ventral area. And then the particles that are not digested, it will be just moving around, floating around the upper part of the rumen, which is called the dorsal rumen. And the large particles, because of this process, large and undigested particles are selectively retained in the rumen for a long period of time, while digested and dense materials can pass out of the rumen quickly. As I said, I developed a model to describe all these dynamics. So I'll show you on the last part of my presentation. And very active fermentation occurs in the rumen, and then through this process, ruminant animal obtain energy and protein they need for their lives. Okay, and approximately 90% of carbohydrate digestion occurs in the rumen, and 60 to 75% of digestive energy is derived from fermentation in the rumen. So it's quite a lot. So, well, in order to understand the nutrition of ruminants, we have to decipher the biology and the science of the rumen. Carbohydrates are mainly converted into VFA, volatile fatty acids, by rumen microbes. And then the total VFA concentration in the rumen ranges from 70 to 130 millimolar. And the three major VFAs are acetic acid, and propionic acid, and butyric acids. And then their role are a little bit different. So acetate acid is used for energy and fatty acid synthesis, so it's directly related with milk fat. And the propionic acid is used for the glucose synthesis, and the glucose is needed for lactose synthesis. And then this lactose is very important in milking cows, because lactose is related. The amount of lactose in milk is maintaining. So because of the osmolality, so if we increase the production of lactose, then we can increase the milk yield as well. And butyric acid is extensively metabolized in the rumen epithelial cell, and then used for the energy and the fatty acid synthesis. Okay, it's probably already know that relative proportion of these three VFAs are determined by actually the forage and the concentrate ratio in the diet. And this table shows the effect of the forage and concentrate ratio on BFA production and ruminal pH. With high forage diet, so low concentrate diet, the acetate and propionate rate, so we call it AP ratio, acetate propionate ratio, is about 4 in this figure. And then in a high concentrate diet, the acetate, proportion of acetate decrease, while the proportion of propionate is increased. So AP ratio is decreased to like a 2.4 in this case. And irrespective of the relative proportion of each VFA, total VFA is always higher in high concentrate diet. That's why we try to feed more concentrate to the animals, because the high BFA is leads to the higher production in cattle. But we have to be cautious because the BFAs are weak acid, and then it's the pKa is about 4.7. So if we have more BFA production or concentration in the rumen, then we will have lower pH. And then in this case, the high forage diet has 6.5 or around 6.5 pH, and then this case of 6.0. And then always the pH is, we try to maintain the pH higher than 6.2, because the fiber bacteria, the activity of the fiber bacteria decreased linearly after pH 6.2. And then if the pH is less than 5.8, the fiber box doesn't actually active at all. So it will die basically. And not only the mean pH, but also instead of the mean pH, but the duration when pH less than 5.8 is more important. So a duration when rumen pH less than 5.8 is the kind of index of rumen health condition. And with the high forage diet, it's only 10 minutes, but with the high concentrate diet, it's more than 300 minutes. So it's more than 5 hours. So this indicates that this animal has rumen acidosis. Okay. Let's move on to the protein degradation in the rumen. And the feed crude protein is degraded by rumen microbes. And if feed crude protein is degraded, then we call it RDP. It's a rumen degradable protein. And if it's not degradable by rumen microbes, then we call it RUP, rumen undegradable protein. RDP is basically converted into the ammonia, and then ammonia is taken up and used by the microbes for their growth. Okay, and then we call it microbial crude protein, MCP. And then the microbes will pass out of the rumen, and then it will be degraded, digested by the digestive enzyme produced by the animal, and then the amino acids, the end product of the digestion, will be observed through the intestinal wall and then used by the animal. On the other hand, the RUP also can pass up the rumen and then degrade by the digestive enzyme, and they can provide the amino acids. These amino acids, the observed in the small intestine, we call it metabolizable protein, MP. And unlike non-ruminant animal, non-ruminant animals, CP should be enough. But the ruminant animal, MP, instead of MCP should be used, should be considered, because the MP is the what the animals utilize. The ammonia right here, if there is excessive amount of ammonia, then it will be absorbed through the rumen wall and then enter into the liver and should be converted into urea and excreted to the environment through the urine. And during this process, a lot of energy is needed. So if we supply surplus of RDP, this RDP can compromise the energy available for production. So based on the biological background, we developed MP system, protein system, and in the MP system, the protein requirements are partitioned into the needs of the rumen microbes and the needs of the host animals. Okay, for the rumen microbes, there is a requirement for rumen degradable protein, RDP. RDP is only used by the microbes. It is just ammonia or MPN, so the animal cannot use this nitrogen source. And rumen microbes can convert this RDP to microbial crude protein, which the animal can use. And in this case, ammonia and the peptide relative to the supply of a fermentable carbohydrate should be balanced. Otherwise, as I said, surplus amino acid, surplus RDP will compromise the energy available for production. And if it is limited, then it will lead to limited amount of our MCP production. Okay. So for the host animal, there is a requirement for the rumen undegradable protein. So we first calculate how much MP can be supplied by the microbial protein. MCP has 80%. 80% of the MCP is true protein, and which means true protein means it has amino acids. It's comprised of amino acids, and the degradability is 80%. So 64% is the efficiency of the use of the MCP. After that, we calculate the MP requirement for the animal, and then we subtract the MP can be supplied by the MCP. Then we will calculate how much RUP is required for the animal, and then that will be the final the requirement, crude protein requirement for the animal. RDP requirement right here, and then RUP requirement, either sum of the RUP requirement and RDP requirement. Okay, so we have accumulated all this knowledge. I just briefly introduced some ruminant nutrition, the key aspects of the carbohydrate and the protein metabolism in the rumen. So we know we know actually pretty much about it. And then now what? We put together all these things knowledge in a modeling framework. In this figure, okay, this is model, but it's a conceptual model. So a rumen digestion and the metabolism process is shown in the box and arrow, the framework or format. This is basically the basics of a conceptual model. There is a continuous input of nutrients from the outside of rumen, and then some of the nutrients will be degraded by the microbes, and then converted into some form of nutrients, and then those nutrients will be absorbed through the rumen wall. And undigested or microbes or converted, so transformed nutrients will be passed out of the rumen and enter into the lower gut, and then those nutrients, if they can be degraded and absorbed through the intestinal wall, then the animal can use it. This is just conceptual model, but I would like to point out that we need to develop a model, not only conceptually, but also quantitatively. So which means we have to express all these components in mathematical forms. Okay. One of my colleagues, Professor Louis Tedeschi at Texas A&M University, he recently published a paper in the Journal of Animal Science and summarizing all the nutrition history of ruminant nutrition models. And because I was working at Cornell University, the revising the CNCPS version 5 to version 6, so I'm kind of biased toward the CNCPS and NRC. But as you can see, all the arrows are the of these all different models. So all of the ruminants interrelated each other and share some basic concepts because they are based upon the same, the common scientific knowledge. And even within CNCPS models, there are several variations. The CNCPS-based models are CPM dairy, and the industry people heard about it, but may heard about it, AMTS, and RNS, that's the Tedeschi's model. And then I developed my own system. It's called the CNU-CNM. And they all share some basic concept and assumptions of CNCPS, and then I will present those basic sub CNCPS in this presentation. Okay, because the rumen bacteria are the key players in the ruminal digestion, the first step of rumen modeling would be the characterization of the rumen bacteria. And this is one of the strengths of CNCPS-based model. CNCPS actually grouped the rumen bacteria based on their sources of carbohydrate to obtain energy. Fiber degrading bacteria versus non-fiber degrading bacteria. There are 4 species in the fiber degrading bacteria, which are very famous in terms of cellulolytic bacteria. And then they ferment fiber carbohydrate, and they require only ammonia as their nitrogen source. On the other hand, NSC bacteria or non-fiber degrading bacteria use non-fiber carbohydrate for example, starch. And then they can survive only with the ammonia, but if they provided the preformed amino acid, they grow better. Okay, the output of the end product of the fermentation of the FC bacteria is mostly acetate. And the output or the fermentation and the product of the NSC bacteria is propionate or lactate. And then if they grow fast, then they produce lactate instead of the propionate. Fiber degrading bacteria are sensitive to pH. So, as I said, if the pH goes below 6.2, their growth rate decrease linearly, and then below 5.8, they cannot be active. They are just latent. But the other hand, the non-NSC bacteria, they have a moderate or strong to acidic conditions. I need to point out that the growth potential of 2 groups are not different. Actually, NSC bacteria need more maintenance energy than SC bacteria. However, non-fiber degrading bacteria right here grow more than fiber degrading bacteria only because the non-fiber, the fractional degradation rate of non-fiber is faster than fiber. So for non-fiber, the degradation rate of non-fiber is about here, and then fiber degrading fractional degradation rate of the fiber is about here. So we can expect more NSC bacteria in our MCP in the produced in the rumen. Okay. And the model for behavior of ruminal bacteria explains the relationship between ruminal fermentation characteristics and the pH very well. When forage or fiber is sufficiently provided to the animal, these fibers enhance chewing and salivation. And saliva has a buffer, sodium bicarbonate, and bicarbonate is the dominant buffer in the rumen, so which help to maintain the pH in the rumen. And then because of the substrate and also the pH, the fiber degrading bacteria, they are very active in here, this area, and then they will produce more acetate here. If the supply of non-structural carbohydrate or non-fiber carbohydrate increases, non-fiber degrading bacteria becomes more active, and consequently they produce more. Propionate, so proportion of the propionate is increases, and then because the more X's are produced, the pH is decreased. Okay, as the pH decreases, the activity of fiber degrading bacteria decrease, so as the less acetate will be produced. And if we supply more highly fermentable carbohydrates, sugar and starch in to the animal, then BFA and the lactate production increases and the pH decreases even more. And the only lactic acid producing bacteria can survive in this area, in this pH. So no more lactic acid dominant, and then no more bacteria can survive in this area. And we call this condition as a ruminal acidosis, especially in this condition, we call it acute ruminal acidosis. So increasing VFA production while maintaining pH is one of the key nutritional practices in high-producing dairy cows and as well as feedlot cattle. And in order to balance these things, we need to predict ruminal pH better. In 2016, beef NRC only forage content is cleared to predict the pH. So when forage content is less than 50% of the dietary dry matter, then pH is decreased. As forage increases, pH decrease as forage decreases linearly. Okay. And then in dairy cattle, PE-NDF content, if PE content is known, then we can estimate the pH based on the PE-NDF. PE-NDF is physical effective NDF, and then it's measured like dry sieving of the particles, and the particles remain in the 1.18 millimeter screen. Is considered physically effective. Physically effective is related with chewing activity. Chewing activity is related with the saliva secretion. So it's basically the physical effectiveness of a fiber is considered in the physical effective NDF concept. And if PNDF is less than 20% in the dietary dry matter, then the pH will go below 6.2. So like a physical effective NDF of 20% is kind of a key, the limit. Let's move on to fractionation scheme of the nutrients. Okay, one of the key elements in the assessment of nutritive value of feed is how to characterize the feed nutrients. Based on the physiology of microbial fermentation, CNCPS has divided the feed carbohydrate into detailed fractions. Based on the solubility in various solutions. And basically there are three major fractions in the feed carbohydrate, and the A fraction, which is soluble in water, and B fraction, which is not soluble in water but is available, degradable, and C fraction is not available fraction to the animal. First, the CNCPS divides the carbohydrate into two fractions. One is non-structural carbohydrate and the other is structural carbohydrate, of course, because the non-structural carbohydrate is degraded by the fiber bugs. And in NSC, in NSCC fractions, there are A fraction and B1 fraction. And B1 is starch, and A fraction is further divided into four different fractions based upon the chemical and the nutritional perspectives. characteristics. And the B1 and B2 is quite similar in terms of the rate of degradation, but they have to differentiate it, because the solo fiber doesn't produce lactate, which is very harmful in the rumen health. And then structural carbohydrate, the fiber carbohydrate divided into the two fractions, B3 and a C fraction. And C fraction is basically unavailable fraction, and then is calculated as 2.4 times lignin. Okay, this carbohydrate fraction scheme is based on the Van Soest, Peter J. Van Soest detergent system and the model for rumen bacteria. CNCPS also fractionates feed protein based on the solubility in the various solutions. There are 5 fractions, and BA, B1, B2, C, and B3 and C, and those are also based on the solubility in the various solutions. First, there are the borate phosphate buffer soluble protein, and the fraction A and B1 belong to this fraction, and the fraction A is basically NPN, and B1 is soluble true protein, which is comprised of amino acids, and in the terms of the protein is albumins and globulins are main proteins in this fraction. And then within the borate phosphate insoluble protein, there are actually 3 fractions. There are 3 fractions. One is detergent ND-soluble fraction, which is called the B2 fraction. It's the degradation rate of this fraction is kind of intermediate between B1 and B3. And then with B3 fraction is neutral detergent insoluble but acid detergent soluble fraction, and it's very it has a very low rate of degradation. And the fraction C is basically acid detergent insoluble protein, and we assume that CNCPS assume that the degradation rate is 0, but this is not the case. This is not true, so we have to revise this fraction actually. Okay, one of the important feature of ruminal digestion is the dynamics. Ruminal digestion is a dynamic process. There is a competition between digestion and passage. If digestion is so fast, all the nutrients will be digested in the rumen, no matter how fast the passage rates are. And if digestion is not so fast, then even though the rate of digestion is the same, passage rate will be plays an important role. If passage rate is high, then the most of nutrients pass out of the rumen. If passage rate is low, then even though the same degradation rate, the nutrients will be digested in the rumen. So we need to consider both KD, the rate of fractional rate of digestion, and KP, which is called the fractional rate of passage. Okay, and then ruminal digestibility is calculated as KD over sum of KD and KP. Okay, fractional rate of digestion, or KD, can be measured using in vitro and in situ methods. Okay, over the course of the incubation in the rumen, several time intervals with the feed disappearance degradability is measured over time, and zero time measurement is assumed as the initial solubility, and then the incubation lasts until 48 to 72 hours for rapidly degradable the feeds, or 96 to 240 hours, even 10 days for slowly digested components. After we obtain time series measurement of the ruminal digestibility of feed over time, then we need to fit the data to a model to estimate the digestion kinetics, which means KD here. The commonly used model is the first order exponential model. And then in this exponential model, we assume rate is proportional to the amount of substrate. Okay, and for example, degradability at time t is this is the very commonly used model. Use this exponential equation right here, and then after feeding a nonlinear regression, we can estimate all these parameters, including the rate of digestion KD here. Okay. In order to know the digestibility, as I said, we need to know the rate of passage, fractional rate of passage as well. However, it is quite challenging to estimate Kp in an experimental situation. Also, there are so many factors that can affect passage rate. So most of nutrition models use a model to estimate Kp. The CNCPS and 2016 BFNRC adopted the empirical equation by Seo et al. 2006, which is shown here. Okay, and then this model has three different the equations, and for forage and concentrate and liquid. All the Kp, the major drivers of the Kp is intake as a percentage of body weight. So forage as a percentage of body weight, and concentrate intake as a percentage of body weight is the most significant variable determined at the Kp. And this model is called an empirical model because it is developed based on data and statistical correlation. And because of the simplicity of the model, it's used by many models. But with this empirical model, we cannot actually move forward. Okay, we cannot go deeper into the science. If we have enough accumulated knowledge, then we can develop a mechanistic model based on the cause and effect relationship. This figure shows the conceptual model about the dynamics of digestive flow in the rumen and out of the rumen. I developed this model based on animal physiology and particle dynamics. I assume two particle pools based on the size, small and large. Small means the particle is less than 1.18 millimeter. And I also introduced the conceptual pool in escapable pool, physically dorsal part, and the escapable pool physically is a ventral rumen. And then as digestion proceeds, the particle in the inescapable pool, the increase is functional specific gravity. Functional specific gravity is the specific gravity and considering all the gas and the water, and then they will sediment to the escapable pool. And because of there is a current, the particles in the escapable pool can be located in the reticulum. Okay, and there are two passage out of the rumen. And first, passage one occurs together with reticular contraction. And then the material during this passage, the materials located in the reticulum can pass out of the rumen. Okay, and then passage two is there is a passage two is between two reticular contractions. So the consecutive reticular contractions, there is passage two. And then during passage two, the particles, if the particles is located in this area, they can pass out of the rumen. Okay, so this conceptual model was developed first, and then this model was transformed mathematically into a dynamic simulation model. And then I'm not going to show you the whole details of a model, but if we can, we have a knowledge, and if we have if we develop the mechanic and dynamic model based on the animal physiology and particle dynamics, with this model, at least we were able to successfully represent the concept of particle size. The critical particle size concept is based on the observation that 90% of fecal particles pass through 1.8 millimeter screen. Even though this is the kind of observation study, but we didn't know actually what underlying mechanism govern this phenomenon. But with this model, we can represent it. We can explain these things. And then the model also can explain selective retention of forage particles in the rumen. So in other words, the model helped to expand our understanding of the ruminal digestion and the dynamics. And another good thing about this model was it could pretty accurately compare to empirical model. Okay, even though this model is used by all the nutrition models, but this mechanistic model could explain more variations in the KP in the literature. However, unfortunately, this model has not been integrated into a nutrition model yet, because it's the limitation of a nutrition model at this point. Okay, I'd like to wrap up my today's talk with this message. We study and conduct experiments, and based on the knowledge, the information we gathered, then we model the system, okay, and try to predict the behavior of the system. If the model works well, it means we know something. If the model doesn't work properly, then that means our knowledge is not ready yet. It's not complete. Okay, so modeling, mathematical representation of this, the concepts or hypothesis is always very important. And then we can manipulate the system based on the model predictions, okay? And then I'm gonna just briefly introduce the late Professor James B. Russell's list of the ideal rumen fermentation. And then our ultimate goal would be the finding a way to manipulate rumen fermentation based upon our knowledge and our models. So I would like to see a lot of people try to learning and working on modeling. And as a wrapping up, for the better sustainability of cattle production, precision feeding is needed. Precision feeding is to feed an animal to produce desired products efficiently and effectively without excessive amount of nutrients. And for the precision feeding, we need to predict nutrient requirements of an animal and the nutritive value of feeds and integration of this in all of this. And for this, mathematical modeling is essential. And then if we can model our system, then we can probably manipulate the system as we want. Okay. Thank you for attention.